Hello, class. So, today, what we're going to be going through is something a bit more provocative than in our other lectures because it's not necessarily something that's been studied from this point of view in a very standard sense, but it's something I call uncertainty programming, right? Because we've done differentiable programming, which is how can you do derivatives by, doing a programmatic means and a programmatic, transformations to compute derivatives. Then we did probabilistic programming, which is similarly about programmatic transformations for pushing forward probability distributions and handling them. But now what we want to look at is uncertainty quantification under a similar lens and kind of see whether it's a problem that in theory can have similar tools, and what are the tools that have been developed so far, and what are the ways to think about doing uncertainty programming. So first of all, what is uncertainty quantification? Well, uncertainty quantification is the identification and quantification of sources of uncertainty, right? So if you think about in the training of our neural differential equation, we have quite a few places where uncertainty comes in, right? So there's errors in the ODE solve, there's truncation errors in the adjoints as well, right? So the gradients have errors. There's truncation errors in the interpolation calculations in the adjoint solves. There's numerical errors in every single dot product, right? Because remember that floating point arithmetic is never exact. And so when we do the dot products and we do matrix vector multiplications and everything inside of our neural networks, that's introducing an error. There's numerical errors in the back propagation algorithms. There's measurement errors when fitting our data. That's why we have a measurement distribution in the probabilistic sense. Um, there's randomness in the optimizers, and there's also an error in the model specification, right? Like, if we specify that our differential equation for our system is f, that specification could have, error associated with it as well. So the real question is, you know, how correct is my model, right? Is our model something, how much certainty do I have in my result? Is a is quite an involved question. And what we're going to be discussing today are some of the techniques that people use to be able to say, I have some uncertainty in a certain thing, so therefore let me compute with respect to my known uncertainties. So there are two high-level uncertainty quantification techniques that fall out of the methodologies we've already discussed. One is to let f be data and fit. So if we fit a model f to data, like a neural network or a neural ODE or some physical ODE model, we don't need to do that fitting deterministically, right? We don't need to say we fit and find the best values. We can instead fit probabilistically and then use that to quantify the uncertainty in our parameter values, right? Because it kind of gives you a distribution saying like all of these parameters are okay for, they give okay results in the cost function as well. So we don't have a single estimate for the value. We instead have a smeared estimate with a probability distribution for possible values. Um, so another form of high-level uncertainty quantification that we've talked about is global sensitivity analysis, because this gives a measurement for how the output is going to vary over a wide range. And so if you had uncertainties in your model and uncertainties in your parameters, the results of global sensitivity analysis are in theory still applicable, right? Because they aren't making a statement about what happens in an exact case. They make a statement over a large domain of cases. You tend to have behavior like X and tend to have behavior like X goes to Y, right? So in that sense, global sensitivity analysis is then a uncertainty aware method where it's taking into account your possible uncertainties and giving you these qualitative results that you can still trust. Um, but let's see what if we can do something a bit more when we have some known uncertainties. So instead of relying on Monte Carlo methods, right? So you could do everything with Monte Carlo, which we explained in the probabilistic programming lecture, which is if you have input distributions, you can send them through your program by doing sampling of the distributions and then running your program a few 100,000 times, and then do kernel density estimates to get the output. That is an extremely expensive form, though, right? Because you're doing hundreds of thousands of ODE solves just to be able to get the probability distribution of the ODE solution. So, are there ways to be able to compute the solution with respect to the uncertain inputs without having to do a bunch of samples of our uncertain inputs? So one way that this is done is by by reviving some of these old physics rules that you might know. So if you did a physics class where you did some arithmetic with uncertainty, you might remember that you had numbers like x equals a plus or minus b, and you'd have rules like if you did a real number and you add it, if you take an uncertain number and add it to a real number, then you would oh, this is supposed to be alpha plus x, then you would add the alpha to the certain part, right? And you keep your uncertainty unchanged, right? So, if you have error bars around a value, but then you're adding a value without error bars to that, then you would just scale and you keep your error bars the same. If you multiply by a scalar, then you would want to change your error bars by that scalar as well, because if you have an error between if you think your value is 2, but it can also be from 2 to 3 or 1 to 3, and then you say, well, now I'm going to look at 2 times my value with uncertainty, then then the result of that calculation is between 2 to 6, right? So you'd have to multiply your error bars as well. So let's see if we can actually develop this idea of arithmetic uncertainty quantification into a full programming kind of style. So it can kind of think about doing at this like dual numbers, right? Except what we want to do is we want to represent the probability distribution, and it turns out that the normal distribution is the one that's associated with these rules. So interpret that if I had a number x is a plus or minus b, say that this is a value x, which is a random variable drawn from a normal distribution with a mean a and a standard deviation b. Um, from the standard rules of distributions, it would follow that you know adding alpha to a is equivalent to um, adding alpha to a is equivalent to so what I mean here is that let me pull open my sorry about this. So let me pull open my other form of the lecture notes. There we go. Yeah. So what I mean by this is that if we have alpha alpha plus x, and x is defined as having uncertainty to it, so we have that x equals a plus or minus b, then alpha plus x would be alpha plus a plus or minus b, right? So then if we were saying that if we, in another sense, if we had x is a value that is a random number that's taken from the distribution that is normal with a being, then the value that is x plus alpha, right, where alpha is just a real number, this would be taken from a normal distribution of a plus alpha b, right? And this rule right here is actually just the standard rule of probabilities. So if you look at the actual probability distribution of x plus alpha, you can prove that if x follows this distribution, then x plus alpha follows this distribution. And similarly, it turns out that alpha times a goes as the distribution of alpha a alpha b, right? So when we're thinking about this as the standard deviation, so before in the course we were writing the second term as the variance. Here now we want to say that this is standard deviation. And so if it's the standard deviation, then we have to take the square root of the square here, which it where the absolute value comes in. So so what this means is that we can change this to be something about arbitrary values, right? So what is the value f of x? Um, f of x goes as what probability distribution when x is given like normal of a b. Well, it turns out that you don't always get a normal distribution, right? So we saw last time that x squared actually goes as a chi-square distribution. Right, so you can define the distribution for what happens when you square it, but it's very different from a normal distribution, right? Because the distribution of the squares is not going to necessarily be a normal distribution because your probability of being negative is 0. You can't square a real value and get negative values. So you necessarily have different probability distributions from nonlinear functions. But if you wanted to represent it in a way that is, if you want to represent an approximation to this distribution with a normal distribution, how could you go about doing that? Well, let's say that um, f of x equals a times x. Where x goes as a normal distribution. Well, here now I'm saying that it is mu sigma, where mu is a vector and sigma is the covariance matrix, right? So in a multivariable sense, with a multivariable function, multivariable linear function, what would happen if you stick a normal distribution number, normally distributed random number, and then you multiply it by a value a? What you'd have then is what you can show is right. So this is a standard thing that you'd prove on the probability distributions of normal distributions. You can show that the expected value of f of x is going to be a times mu, and um, the variance of f of x is going to be equal to what comes out of the fluctuation dissipation, which is this value right here, right? So if you have a linear function, then the push forward of a probability distribution onto it when that distribution is a normal distribution has a closed form solution. This would mean that f of x goes like a mu, a sigma, a transpose as the new covariance matrix, right? So the interesting thing is that now take any nonlinear f of x by Taylor expansion. We can represent it via an affine method, by affine transformation, right? Let's say that f of x equals f sub 0, so some constant, plus jx, where j is the Jacobian, right? So this harkens back to what we were talking about at the very beginning, which is with dynamical systems, where we say, we can always linearize a function f and then understand its behavior, at least locally, by its linearization. Um, and so, we know how to handle this f0, right? If you have just a f0, then you just add it to the mean, and so so and thus a an approximation for any nonlinear f of x is that f of x is pushed forward by the f of mu, right? You basically can always push forward the mean value, and then um, push forward the covariance matrix based off the Jacobian, right? So you apply f on the mean value, and that is actually going to be the mean value of the output, and then the linear approximation to the covariance matrix is to assume that you replace the action, the nonlinear action, with the linear action of the linearization, where the proper linearization is given by the Jacobian matrix, and therefore the best approximation to the Covariance matrix is done just with this Jacobian Jacobian previous uh, Jacobian times the covariance matrix times the Jacobian transpose, because that's exactly the analog to the previous linear version. And what this means is that if you can get Jacobians and you can push forward Jacobians, then it's possible to push forward normal distributions in your program, just like we were doing dual number arithmetic. And that's precisely what this library measurements.jl does. So it does this kind of programming approach, right? So this approach of defining algebras and computing on algebras to be able to push forward values that have normal distribution types of arithmetic and push this through entire functions, right? If it doesn't know how to deal with a composite function f, it does the same trick where it just kind of thinks a program is a function f, but you can represent that as a series of stages, right? As a series of stages. Uh, so that way you can say, oh, if I don't know how to do the push forward of f because I haven't predefined how to get the Jacobian and do it on this operation, then what I can do is I can say that a program is a composition of functions. And if I know how to do the push forward on every subfunction, then I can push forward a probability distribution through your whole program by doing it along each step of the way. And so we can look at this on something like a differential equation solve, right? So this library has predefined how to do the push forward through operations like sine, cosine, plus, minus, multiply, divide by using this rule to be able to derive how to push. If I have a plus or minus b, then what would the output with uncertainty be through sine, through cosine, and all that. And so what you can do then is you can take in a whole ODE solve, decompose it into steps, and do the push forward through each of the steps. So here what we can do is we can say, let's use ordinary diffeq, the differential equation solver with measurements. Um, let's make our gravitational constant be something that has uncertainty associated with it. Let's make our length of the pendulum be something with an uncertainty associated with it. Let's make our initial conditions to the ODE solver be something that have uncertainties as well. Here is my ODE. Here is my problem. Now let's solve this problem. And the output when you plot it is it has error bars everywhere. Because the solution to the ODE has the error bars that are induced by pushing all of these probability distributions through it and getting a normal distribution at each point in time for what the probable output is. You can see that over time you're getting increased more and more uncertainty as the uncertainty in the gravitational constant is making us less and less sure where the probability distribution will be. Um, this also kind of highlights another feature to kind of think about, which is the plots.jl recipe system. I'm not going to go into too much detail on how this works, but what is really doing underneath the hood is it lets you define how to do plotting through program transformations. Right, so the way that this plot recipe works is that the differential equation solution has a plot recipe that says if you see a differential equation solution, then take the solution, the time series of the ordinary differential equation, turn those into arrays by interpolation, and that is what you plot. So it knows how to transform the output type of solve into arrays. But then you have arrays of uncertain values, and there's a plot recipe in measurements.jl that says if you see uncertain values, change those into arrays of floating point numbers, and then but also define a floating point number for what the error bars are. Right, so you can just define one step of a transformation in the plotting function, and then when you say, okay, let me plot an ODE solution of quaternions with uncertainty, different programs are just choosing how to do transformations of one small part of it. And when you compose together all those transformations, then you get plots that happen automatically on complex types. So this is kind of like a nice display here where we're doing computations with uncertainty. We're getting output values with uncertainty, but you don't have to really spend much time to be able to plot it because it's just kind of handled by the system by doing a very similar approach to code composition. But this kind of is a very nice idea though, because this means that, without having to do Monte Carlo methods and, sample all these input distributions many times and solve a bunch of ODEs, here we have a single ODE solve that outputs, a solution with uncertainty. And so this is much more efficient than doing these sampling kinds of approaches. Now, it does have some downsides because this is doing a linear approximation. Linear approximations are not exactly, correct. They have a certain error associated with them as well. And so you can actually find some cases where this blows up. A package which has come out, which is very useful in this case, is Monte Carlo measurements.jl. The Monte Carlo measurements.jl is an extension to measurements.jl, which also allows embedding Monte Carlo particles and doing a very and doing a full push forward approach. And if you want to see some counter examples to the linear uncertainty propagation approach, check out this page in the Monte Carlo in the Monte Carlo measurements uh, documentation, which kind of showcases some places where, using measurements can go wrong. And actually, I'll highlight this on one of these examples here too. So essentially, what's going on in the uncertainty here is you aren't actually getting more uncertainty in the up down direction, right? Like you kind of are, but truly what's happening here is that when you change the gravitational constant, the phase or the wavelength of the pendulum's, periodicity will change, right? So this wavelength is either getting wider or shorter. And what this means is that, if this value is actually supposed to be to the left, then, so if this value is supposed to be to the left a bit, that's why this interval is growing. But what you can see then is that this interval is sooner or later is going to grow to be from 0 minus 1 to 1, saying that you can be anywhere in here. It's just you don't know the phase of the solution. But for any given solution, you actually can have a lot more information than that. So what I want to show um, in one of the later parts of this is exactly how, if you represent trajectory wise uncertainties instead of, lumping together all of your uncertainties, you can have quite a bit more information than that. So let's hold on to that idea for a bit. But first, let's look at interval arithmetic. So interval arithmetic is similar to measurements, but it's about doing measurements in a numerically exact way, right? So, measurements.jl is all about, if we have input uncertainties, then how would we try to compute the output uncertainty? Interval arithmetic is about, if we think our computation is correct, but we think that there's also some numerical error to it, right? Because there's always numerical error. How can we represent the possible values that could be coming out of our program if we take into account all of the possible numerical errors that are occurring inside of our program? So interval arithmetic lets you compensate and account for all of the possible floating point error. And then what it's really doing then is it's computing by sets. It's saying, if I have the set from A to B, this is all possible numbers in R, um, from the value A to the value B. And so what interval arithmetic lets you do is it lets you represent this interval in a very nice way, and it lets you then do computations on this interval. So you can do something like, say, what is x, my interval x plus 1? Well, my interval x plus 1, the possible results of x plus 1, if I look at every single value in the set, is that it's, 1.01 to 1.02, right? And you rigorously can make that statement. If you have round off errors, you have to make sure that do you have to make sure that you round down on the left side, and you have to make sure you round up on the right side, so you conservatively include the entire set of possible real numbers, right? So it's always going to give you a conservative estimate, but you know that the true solution with respect to, no floating point error will live inside of that interval that it gives you out. And so you do have to work out what happens on, for example, non-monotone functions. And so if you square an interval from A to B, well, you have to, check the case of whether you have one thing negative or two things negative. So there are a lot of rules to work out. But once you work out the rules for, the arithmetic for what happens when you do f of x on given intervals, then you can start to run intervals through entire programs just by thinking about it as a composition of steps and doing the arithmetic, the interval arithmetic through each and every step one at a time. Um, so you can actually use this to prove theorems rigorously. So you can say h of x is equal to x squared minus 2. And so how would I prove that h has no roots in the interval 3 to 4? Well, if we stick the interval of 3 to 4 inside of it, then we actually see that the output is the interval from 7 to 14, which means that there is no way for h, when you have an input from that real number between 3 and 4, there is no value for for x in this interval such that h of x is equal to 0, because every value of h of x with input of that with x in this interval has to fall into the range of 7 to 14. And so, because it is actually giving you these conservative intervals that always are rounding up and rounding down, so that way it includes the possible output, this actually gives you a nice way to be able to prove certain statements, like whether it's possible to have a zero in a given range. One of the issues with interval arithmetic, though, is that it's conservative at every single step, which is what gives it its rigor. But because it's so conservative, you can actually easily find cases where your intervals explode to infinity, and they kind of start to make the trivial statement that your program solution is between minus infinity and infinity. So let's look at a case of that. So let's say we have intervals instead of measurements for our input uncertainties, right? If we're using intervals for our uncertainties instead of measurements, um, then what this kicks out is you can actually see that the first interval is not too bad, but these intervals start to grow over time, and by the end we're having something say that our pendulum is somewhere between minus 400 and 400. That is rigorous. I mean, that is correct. Our pendulum solution, because it's between -1 and 1 by construction, right? We know that the analytical solution to the pendulum ODE, um, it is truly between these values, but you can see that being conservative at every single step and always rounding in the way such that you know it's going to be in the interval. If you do a lot of floating point operations, you can end up with intervals that are quite large. So I mean, you could play around with this, and you can say, I can constrain my intervals to be smaller. So actually, let me say that I have instead of having uncertainties in my input, right? Let me just say I have no uncertainties in my input, but I want to just capture the possible floating point round off error. Well, then I can say I have an interval where my input is a 9.8. I have an input which is with an input length of the pendulum, which is 1.0. Run it through with interval arithmetic, and then this tells me that I have, your possible values for your pendulum are somewhere between -7 and 9. Right, that's still too conservative in this case. So, there are cases where interval arithmetic works very well, but when you tend to have things like matrix multiplications or a lot of repeated operations, your intervals might blow up too large to be an effective tool for really the analysis you're doing. So, interval arithmetic is great because of its rigor, but also it's not great because of its rigor. So, so that's one thing to keep in mind. It there it always measurements.jl is giving you a probabilistic statement about intervals, and so it doesn't necessarily mean that with 100% certainty the true value of the pendulum is in these error bars, but it says with a high degree of certainty this is where the solution lives, whereas the interval arithmetic is giving you an interval where it says with 100% certainty the solution is inside of those intervals. But in order to have that certainty, the intervals need to be growing at a faster rate. So now let's look at some contextual uncertainty quantification, right? So those methods for uncertainty quantification were program independent, right? Like you can take any possible function f and you could do those uncertainty quantification techniques to be able to give you a way to be able to push forward uncertainties through your program. Well, now let's look at something a bit more contextual, right? This actually kind of gives a lot of ideas for how you might want to do uncertainty quantification in more specific contexts. Let's look at quantifying the uncertainty in ODE solvers with adaptivity. So you did a homework problem where you looked at one of these kinds of tables. So this is the Dorman-Prince method, and you use the steps along the Runge-Kutta method to compute the output, right? But there's a second row to this table. So how do people make use of that to be able to do an adaptive ODE solve? Well, what you do is you compute all of these steps. So you get K1, K2, K3, K4, K1, K2, K3, K4, K5, K6, K7, and then you do a linear combination of the K set of all the Ks against the Bs to give you your step, right? And then that's what you did in the homework. Now here's another set of Bs that you could do a linear combination with. And this is actually known to be a fourth order method. So this is a fifth order method, but if you use these other coefficients, you get a fourth order method. Um, so what you can do is you can show that, if you take the difference between a fifth order method and a fourth order method, you actually have a way to be able to estimate the error, right? Because one of those methods is a bit less error prone than the other. And so the difference between them is actually a good O of delta T estimate for what your possible error is. And so this is what the actual methods will use. They'll say calculate K1 through K7, and now calculate the next step of your OD using these coefficients, and calculate the embedded step using these coefficients, and the difference between their prediction for where you'll be in the future. That difference is an error estimate E. And you can prove rigorously that it's a good error estimate, given that these are both stable high order methods. And so what you do in adaptive ODE solvers is you say, if I have an error of E and I want to hit a relative tolerance and an absolute tolerance, I can make my Q be this formula, and then my next delta T should be Q times delta T, right? But let's think about if we have a relative tolerance of 0. Let's see what that means. If you had a relative tolerance of 0, what this would mean is that if your error was 2 times your tolerance, then this would tell you that you'd want to half your delta t. So it's a proportional control method where you are controlling your delta t proportional to the to the ratio of the error to the tolerance. So this is a kind of standard way. There's a lot more depth you can go into these error tolerance calculations and the way that you do adaptivity, but that's a very quick overview. So instead of using that to adapt tolerance, could we use this to propagate uncertainties? So there's something called the Probins method, which says E gives us a sense of uncertainty in every step of our ODE solver. So what we can do is we can say, instead of solving an ODE, which is deterministic, what we can do is we can say, when we actually see our ODE solver gives an output of UN, right? The possible values it could have had is anything of UN plus E, where E is some normal distribution with standard deviation of this error estimate, because that is the estimated error we think we have, right? Like just because we put out U of n doesn't mean that U of n or UN plus 1 is the next value. It could be UN minus E over 2 plus E over 2, right? But the relative amount of uncertainty that we have in one step is given by this error estimate that is computed already for the adaptivity. So what we can do is we can jiggle our ODE solution with respect to the known uncertainties in the adaptivity to be able to give us an ODE solution with all of the possible numerical errors associated with it. And this is called the Probins method. Let's take a look at this in action. So here's the Fitsu Ngumuru ODE. What we can do is we can say, let's solve the ODE, but we can also say, let's solve it where we're adding in noise, which is going to be using the adaptive province method. It needs to know the order of the ODE solver, but what we can do is what this is doing is that every single step is going to look at the internal error estimate of the adaptivity and say, now let's perturb our ODE solution by that error estimate in some rigorous way. Um, and so you then have to run you then have to make sure that you run the ODE solve like 100 times with this perturbing callback in there, so that way you see possible different trajectories with respect to this noise. And here, what it's saying is that at the default tolerances, you can be quite certain about your solution, because if you look at all the possible results you can have given this size of error at each of the steps, then these are all the possible solutions. Um, so what this is telling us is that with the default tolerances, we have a fairly good solution. So let's look at what happens if we decrease the tolerances, right? So let's say we have a very or very high tolerance ODE solution. We're allowing a lot of errors. What are the possible output values? And this is what happens when we say let's have an absolute tolerance of 1e minus 3 and a relative tolerance of 1e minus 1. Um, what we see is that, for example, the ODE solution might not have dropped as far as we thought, or or it might be starting the next transition earlier than we thought, right? But the interesting thing about this is saying that the points at which we have the most uncertainty in our numerical measurement are exactly these caps, right? The at these point caps, we have a lot of uncertainty, but then it kind of, it folds back in, right? So we have a lot of uncertainty at the cap here, or at this kink and this kink, but between them, there's a lot less uncertainty. So we have, we get this spot quite easily wrong, but when we're going back to this flow, there's a lot less uncertainty again. This part has a lot of uncertainty. This part has a lot of uncertainty. So whenever we have one of these sharp transitions in this ODE solve, there is a lot more uncertainty than these other portions. And so by looking at this, we can see that, the there is a growing uncertainty, but that uncertainty is more so the uncertainty in where the corners are, and the uncertainty of how long these transitions take, right? And you can see that through the trajectories. Now let's think about what would have happened if we just tried to represent the uncertainty at this point by an error bar. Well, we'd have to say that the solution at this point in time is anywhere between here and all the way down here. And you can see that if you're to then represent everything as via error bars, after we get to about time t equals 7.5, our error bars are going to be the entire solution. And that's what I was mentioning can go wrong with measurements.jl, right? It can explode these error bars to then say that because you have an error in the phase, it can have a complete error. But here, what you can see is that, if you look at the trajectory-wise uncertainty quantification, you can get much better information. So, for example, an error bar would say that you can be anywhere between -2 and 2, but the reason is because once you have a big error bar here, your error bars always increase, and so it's increasing to here. Whereas in reality, are the trajectories have a lot of uncertainty here. They fold back into a normal flow when they get to this portion, and so you should be increasing uncertainty, but then decreasing as you get through here. And linear uncertainty analysis is going to be missing that effect. Um, so this kind of shows you that there's a lot more that can be done in uncertainty quantification, right? This kind of idea of pushing forward uncertainties with linear objects is not necessarily capturing the full picture, and it's missing a lot of these subtle details about what can happen inside of trajectories. And so there's a lot more that could be done in this field. There are some methods which are done. So for example, there's this polychaos.jl package, which is for polynomial chaos. Which is a way to represent and push forward more general probability distributions other than normal distributions. So there is a lot of work that's being done in this domain. So what I want to end with here is, so this has all been about pushing forward probability distributions. So in a sense, this is all saying, if I had an uncertainty, what is the uncertainty at the output of my program? And now let's compute and understand the result of my program by looking at its probability distribution. But if you think about what we did with things like differentiable programming, the first thing that we did was say, let's take our derivatives and push them through our program. And then we had this brilliant idea of let's take their derivatives at the end and pull them back through our program. And we got a lot more efficient computations, right? So what we can ask the question of is, what is the adjoint of uncertainty propagation, right? So in order to phrase that, what we're going to need a little bit of operator formulae and the way to think about this is that on a dynamical system, the push forward of a measure is known as a Frobenius-Perron operator. So if you had some program S, and you take your input distribution and you want to represent the output distribution, the if your inputs follow a probability distribution f, then the Frobenius-Perron operator applied to f is the probability solution distribution of the output of your program. So let's say we want to calculate the expected value of a cost function on the solution of the program. So the way that you do that is you'd calculate the expected value of the cost function on the solution of the program, where the outputs of the solution of the program are given by push forward all of your densities to be able to get the probability density of the output, and now calculate g, your cost function on these probability distributions on the output of your ODE solve. What I mean is that you have you have a probability distribution over the outputs. Now, if you want to find the average value at this point of the program's output, you can look at the probability distribution of the program's output, and you can actually just take the average of them. So that's what this method is doing, right? So the Frobenius-Perron is saying push forward your probability distributions to go from the probability distribution of your inputs to the probability distribution of your outputs, and then calculate the cost function or the expected value of the cost function on the program's outputs by using that probability distribution that you've calculated. So the Frobenius-Perron method is essentially a mathematical way of encapsulating, the Monte Carlo method, where you're pushing forward and you're calculating distributions. But this also handles the idea of measurements.jl, where you have an uncertain distribution to start, and you calculate the distributions of the ODE solver's outputs, and then you can evaluate cost functions with respect to uncertainty. On the probability distributions of your ODE solution. Right. But computing entire probability distributions is hard. So if you only care about the expected value of cost functions on the uncertainties output, right? So for example, you know, if you want to do something like optimize the parameter values such that when you take into account uncertainty, you have the lowest chance possible of the ODE solve going above one, right? So you can optimize not just to not go above one, but you can optimize with respect to probability, have the lowest probability of going above one, right? So this is called optimization under uncertainty. And one way to do that is to every single time that you have a parameter value, you can add your uncertainty distribution around that. You push forward the uncertainty distribution, and then you calculate the probability that something occurs, and then you can take the derivative through that, and then optimize, and then you'll end up with good parameters, right? But that's really expensive because that means every single time you're doing a cost function evaluation, you're doing 100,000 ODE solves to be able to compute a probability distribution on the output. So is there a more direct way to get the expected values of the output? And it turns out that there is. So instead of pushing forward the probability distribution, what you can do is you can pull back the cost function to the original probability distribution. And the adjoint operator of the Frobenius-Perron is actually a well-known operator, which is called the Koopman operator. And this idea is essentially then that instead of calculating the integral by instead of calculating expected values, by pushing forward probability distributions and doing the integral in the output space, instead pull the cost function back to the input space and do the probability distribution calculation on the input probability on the input probabilities. So what that would mean is that you take so you can take a uncertainty distribution, push it through your program, and then you can do the inner product against the cost function to give you the probability of a cost happening or an expected value of a cost. Or what you can do is you can pull back your cost function to your original probability and do the computation there. What this would actually amount to is your sample. You take samples from your space of probable inputs, and then you define this integral where what you would do is you would take that value, you would run it through the ODE solver to get the solution, and you calculate the cost on that solution, and then you multiply the cost of that solution on x by the probability of seeing x, and then the integral over that over all probabilities is another way to calculate the expected value of the output distribution. And if you do that, you can have a much more efficient way of doing probability optimization under uncertainty. You can see this paper where we showcase optimization under uncertainty of ODE solves. So we do this problem of saying, we want to hit this spot of the wall, with a bouncing ball. So this is a hybrid ODE where there's events handling that's going on and all sorts of uncertainties. But given all the uncertainties in our system, what parameter values should we have for the initial condition such that we would have the highest probability of being nearby this point in the future? And for these kinds of statements, you can get a over 1,000 times faster computation by not computing the probability distribution in the output, but instead doing direct computations of the expectations by using this Koopman operator approach. So in some sense, this is like the adjoint of uncertainty propagation, right? So the Koopman operator truly is the adjoint of the Frobenius-Perron operator, and the Frobenius-Perron operator is the push forward of our uncertainty measurements. So hopefully this kind of gives you some ideas for how to approach uncertainty programming or uncertainty quantification as something that's similar to differentiable programming or probabilistic programming.